Okay, so I'm going to speed through a few slides and talk a bit about what's new and latest from IBM Quantum. So, yep. So basically, I hope you all know by now we have the roadmap. I'm not going to spend any time today talking really about hardware, but I'll say a few things based on the roadmap. First, we've got a roadmap that goes out to basically now 2033 that includes error correction. I'm ecstatic to see that people are finally taking on the quantum LDPC codes and things like this. It's definitely a viable path forward. Second, our roadmap also is focused on how we build tools to simplify running quantum algorithms, and that's what I'll say more in this talk today. And then thirdly, we're very committed to making sure that as we progress on this roadmap, since I put it out in 2019, we've continually ticked off everything across it. So from my perspective, I don't see any roadblocks for us achieving our goal on our hardware of getting to continuing the progress to larger and larger quantum systems. So I want to go to a different direction now. And one of the things that when I think about computing, it's that I trust the output. So one of the things that I want to try and convince you of is we're now at a point we can start to trust QPUs. We can trust that they can execute quantum circuits. Last year, we put out this paper. Basically what it was is a way in which we could do a technique we called error mitigation that allowed you to run circuits that are essentially of 127 qubits, get expectation values with error bars, and basically get at a point where you're beyond brute force simulation of these quantum circuits. What do I mean by that? Imagine I was to give you an experiment, and there's about 8 different black boxes there, and I was to say, I'm going to come up with some observable and some parameterization and basically plot them out. And what happened in this, and this is adapted from one of these papers, is they plotted many different methods. And if you were to look at this, you would actually say for this observable, which is on the y-axis and the parameterization angle on the x-axis, you would say, first of all, they're basically all, sorry, animation didn't work, but they're all different. If you were to calculate how different are they, they're all about 20% different. And the exciting thing is, one of them is run on a quantum computer. So one of them is run on a quantum computer, and the rest are approximate classical simulations, known in the field as tensor methods or matrix product states. So we're at the point now where we can run things on QPUs where you cannot do brute force. The accuracy of what you can actually get out of them is on par with the accuracy of what you can do with approximate methods. This is what we meant by utility. We mean we're in this new era where we can think of a quantum computer as being a useful scientific tool. Since then, basically there's been something like 18 different papers looking at different basic size experiments, running 100 qubits, a couple of thousand gates, and I think I would say the momentum's here. We're definitely seeing it. So when I think of this, I think of basically how do I get trust is I start running many different things on large scale, 100 plus qubits, where I'm beyond brute force, and looking at the results starts to lead to accuracy, it starts to lead to trust. And so I think that this is the most exciting part, is we're in this utility. Where we go forward, how we transition from utility to what I call quantum advantage, I don't think it will be done by IBM alone. I never have. This is why from day one, we've had a very large community. We call it the IBM Quantum Network. That community has over 276 members, ranging from industry experts, like industry leaders, research institutes, startups, nonprofit ecosystem partners, but more importantly, it's people. It's people that are committed to actually working hard and understanding what to do with a quantum computer. So what are some examples of the research that have happened in the network? I'm not going to go into too much detail, I'll flash some up, but then I want to transition to where I see some exciting directions going forward. Like for instance, this paper by University of Washington, they consider the problem of, can I take a quantum computer to simulate high energy physics? If we could actually look at Hadron and not build large colliders and actually simulate it, what would we see? In this paper, they actually got up to 13,000 gates. That's a huge number. And even interesting, at the end, the difference between the matrix product simulation and the quantum system was systematic, and they could not even conclude which one was right. We're at a point where there's science to be done. The same was done with our colleagues at RECON. They looked at this time crystal and they wanted to understand these different between basically disorder and a periodic function. And they looked at different parameters of this kicked Ising model. And at certain parameters, they claimed that the tensor methods were starting to break down. And they could start to see interesting dynamics. Then with Moderna, I am no expert in mRNA and don't ever plan to be, but they started to ask the question, can they actually look at the secondary structures of these to make predictions on how they would scale? And this allowed them to go on to 80 qubits and push basically QAOA type experiments to the limit. And so when I think about this, I think about what's needed is algorithm development. And what we've done and what we've transitioned is we've transitioned Qiskit, which is our open source project, to basically be how we see algorithms getting done. It's got to be Qiskit plus our QPUs is where I hope we will do work. As an example, when I think of algorithms, I think there's like 4 essential steps. Iterate over them, put them together in different ways, but how do I come up with a way of mapping the problem efficient to a quantum computer? How do I come up with a way of then optimizing it to run on a quantum computer? Obviously, I have to execute it, and then I have to do post-process. We've even released AI-powered tools that do this compilation now. We call it a Qiskit transpiler service that it can give you much more efficient quantum circuits. But more importantly, as an example, this work, I'm sorry about the fonts, by Q-Control, one of the partners, I think is an amazing result. They have taken a way to come up with novel ways of replacing the algorithm, to optimize it, to execute it, and coming up with a way of post-processing the results that are efficient to run optimization problems of the order of 127 qubits, a few thousand gates, and they were able to get accuracies that are 1,500 times more accurate than other technologies such as annealers, and 9 times more likely than other technologies in the iron base at looking at optimization. But you put all this together, one of the big announcements we're making is by the end of this year, we are going to start to create what we call a functions catalog, where we will start to see that this notion of a single company or a single person being a full stack is incorrect, where different software will be added. We will have some of our verticals, but you'll start to see, I think this will be as big as an announcement or big as change as when we put the quantum computer on the cloud, when everyone started programming quantum circuits, is we're moving from circuits to what I like to call programming functions. So easier ways for enterprises to use it. And so a way I kind of think of it is essentially application software plus Qiskit plus QPUs is where people can start to do useful work, start to make it easier to program it. So that's the first kind of announcement that I see us moving from circuits to the next level of abstraction, which I call functions. Another area that I want to quickly touch on is quantum-centric supercomputing. To me, quantum-centric supercomputing is not just a larger quantum computer. It's actually much more profound. And what I want to try and convince you and show you of what exactly do I mean by that. So if you take this sort of simple way of understanding algorithms and you say, can I increase it to using parallel classical computing, like running lots of advanced HPC? Or can I do it to running many quantum circuits? You actually start to see you've got to come up with an architecture that mixes HPC, and in the future GPUs, and QPUs together to actually execute it. And like everything, we talked about this a while, but the best way is to show through a demonstration. So with our colleagues at RECON, we asked a question, and University of Colorado, Boulder, we asked a question, can you come up with an algorithm to diagonalize an energy, so find some energy of a chemistry problem, where you do most of it on a quantum computer, and then you do the rest on a classical computer. So you first come up with a way of projecting to a lower subspace. Then once you're in this lower subspace, you can iterate and post-process it and get an answer. There's a lot of, and if you think with those steps, and you zoom into the math, which I don't have time, there are a lot of steps that go into it that like sort of do in principle some form of error mitigation, correct the results. But you can think of it as essentially, now you have a QPU, you have a HPC, you're sending large amounts of data. So in this case, they ran on 77 qubits of our latest Heron processor, doing something like 3,500 gates. They use 6,400 nodes of Fugaku, which is, I think it's the 4th largest supercomputer in the world at the moment. And so now they basically got this quantum computer projecting onto it, feeding the data into a HPC to do the rest. And honestly, I would not have thought chemistry problems of this size would have been possible. The teams were able to look at N2 and actually project and look at some of the architecture. So N2 is known for approximate classical methods to be very unstable to predict distillation. And the quantum result actually worked to do it. For the experts in the field, a method that is the workhorse of chemistry, DMRG, we're actually getting at the limit of DRMG for this iron 2 sulfur 2. And as we extend to iron 4 sulfur 4, we still have a quantum signal. We've got a lot of work. That's at 77 qubits. There's more work in how we're going to come up with better algorithms and analysts. Namely, can we iterate? So in this one where we have basically the quantum computer and we have gigabytes of data and run it on a HPC, there's no iteration. And so can we iterate to make this algorithm work? And that's why we are on our way to actually installing a quantum computer right next to Fugaku. So we can explore how the iterations of these algorithms work. So we can actually push us to the limit. With RPI, and I think you'll hear later from the RPI president, we're doing the exact same in a university that has an 8 petaflop HPC processor, so they can explore that work. And I'm excited because this announcement we just made today, if you do this architecture right, this architecture will not just be dependent on superconducting qubits. So we are creating this architecture for what we call quantum-centric supercomputer, and now we've just announced with Pascal, a leading neutral atom company, how to create this architecture together. So as we go forward, I really think you're going to see this future of quantum-centric supercomputing, and if I was to bet, that's where I think we'll see quantum advantage first. How using both HPC and quantum are put together with a lot of novel algorithms. Just to end, if you want to get started using it now, we already have what we call Qiskit service, where using cloud-based classical compute, you can start to run those quantums. So you see this sort of change of workflow where you basically write your program, you upload your program, you choose whether it's running on the cloud or on a quantum, and then you execute it. And what you see in this sort of architecture is this coming together of this future of quantum functions, quantum-centric supercomputing, to actually take us from executing low-level quantum circuits to what I like to think is the next level as we go towards algorithm discovery. And in a very short talk, I hope I covered the points. The ones I would like to summarize is that I see no stop in the hardware first. Second, we're getting to a point where quantum circuits are probably still used at the bottom, but we're going to start to abstract them towards the functions. And then this new architecture of quantum-centric supercomputing is where I think we'll bring all this together. So I think I have a few minutes for questions.